In this lecture, we examine quadratic functions. In the last lecture, we studied polynomials of a simple form, f of x equals mx plus b. The so-called linear functions were functions of degree 1. Now we move on to a more interesting case, the polynomials of degree 2, the quadratic polynomials. Quadratic functions will have the form f of x is a times x squared plus b times x plus c, where a, b, and c are real numbers, and we'll assume in general that a is not 0. The graph of a quadratic polynomial is a parabola. All of the graphs of the quadratic functions can be created by transforming the simple parabola from y equals x squared into the other forms. Just as we have standard form for the equation for lines, point slope, slope-intercept, symmetric, and so on, we also have a standard form for a quadratic function. Every quadratic function can be put in the following standard form. F of x is a times a quantity x minus h all squared plus k, where a, h, and k are constants, in other words, real numbers. So the standard form for quadratic polynomial looks like this, where we have this quantity x minus h this squared multiplied on the outside by a, and then we add k. From our understanding of transformations, beginning with the simple parabola y equals x squared, if we shift that parabola to the right h units, replacing x by x minus h, and then stretch it vertically by a factor of a, that is multiplying on the outside of the parentheses by a, and then shift the parabola up k units, that is adding k on the outside of the parentheses, we'll have the graph for the new parabola y equals a quantity x minus h squared plus k. This describes how to go from the parabola y equals x squared to our new parabola. The turning point, 0, 0, on the parabola where y equals x squared, is called the vertex of the parabola, and it's moved by these transformations to the new vertex, h, k. If we're given the equation f of x equals ax squared plus bx plus c for a quadratic function, we can change the function into the above form by first factoring out the term a so that it looks like this. On the right side, see that a has been factored out, and then we complete the square on the expression inside the parentheses. To do this further, I need to explain completing the square. A major tool for solving quadratic equations is to turn a quadratic into an expression involving a sum of a square and a constant term. This process is called completing the square. Recall that if we square a linear term like x plus a, we will get the quantity x plus a squared is x squared plus 2ax plus a squared. Most of us are not surprised to see the x squared on the right or the a squared on the right in this expression, but that 2ax, the cross term, is a critical part of our answer. When we expanded x plus a times x plus a, we summed ax up twice. It shows up as 2ax. That 2 is important. Here's a test of our understanding of the simple equation. The quantity x plus a squared is x squared plus 2ax plus a squared. Let's fill in the blanks in the following problems. Here, x plus something squared begins x squared plus 4x plus something. Or here, x plus something squared is x squared plus 10x plus something. In each case, we're going to fill in the blanks by focusing on the cross term, the coefficient of x. The coefficient of x is 4 or 10, 2 or minus 2. Maybe it's minus 6 or positive 7. In each case, we're going to use that to guide us on how we fill in the blanks. For example, in the top equation, since on the right we have x squared plus 4x plus something, then that a part must be a 2. We must be getting like this. We must have the quantity x plus 2 squared is x squared plus 4x plus something else. The final 4 is forced on us. In the next case, take 10 and divide it by 2 to get 5. So we're looking at x plus 5 squared, and if we do the algebra, we get a 25 at the final side on the right. In problem 3, take that blue 2, divide it by 2, it must be a 1, square it to get the 1 on the far right side. The next one is x minus 1 squared will give us x squared minus 2x plus 1. In number 5, minus 6 divided by 2 is minus 3, so we must have x minus 3 all squared. That forces a 9 in red on the far right. In the last one, just as before, we divide the blue number by 2, 7 divided by 2 is 7 halves, so we know we must be working with x plus the 7 halves all squared. Do the algebra. X plus 7 halves all squared is x squared plus 7x plus 49/4. If one understands this simple idea, then we can predict the square by looking at the coefficient of x. Then we can rewrite any quadratic polynomial into an expression involving a perfect square. For example, if you give me x squared plus 4x plus 4, and I recognize that it's x plus 2 all squared, then any polynomial that begins x squared plus 4x must involve x plus 2, the quantity squared. For example, if I take that top equation and subtract 4 from both sides, then I recognize that x squared plus 4x is the quantity x plus 2 squared minus 4. Anything that begins with x squared plus 4x will allow me to replace that x squared plus 4x with x plus 2 all squared minus 4. So, for example, x squared plus 4x plus 7 is x plus 2 squared minus 4 plus 7. In other words, x plus 2 squared plus 3. Or x squared plus 4x minus 5 is x plus 2, the quantity squared, minus 9. Another example, since x squared minus 6x is the beginning of x minus 3 all squared, in other words, x squared minus 6x plus 9 is the quantity x minus 3 squared, then x squared minus 6x is, subtract 9 from both sides, the quantity x minus 3 squared minus 9. If in the first equation x squared minus 6x plus 9 is the quantity x minus 3 squared, then subtracting 9 from both sides allows me to write x squared minus 6x is the quantity x minus 3 squared minus 9. Always stick to the algebra. This allows me to write x squared minus 6x plus 2 as the above equation in which I've added 2 to both sides, so it must be x minus 3, the quantity squared, minus 7 instead of minus 9. Or we could add 10 to both sides of the equation in blue and get this equation. Or we could subtract 3 from both sides of the equation in blue and get this equation. Anything that begins with x squared minus 6x can be guided by the equation in blue. One more example. X squared minus 3x is the beginning of something involving x minus 3 halves all squared. In other words, x squared minus 3x plus 9/4 is x minus 3 halves all squared. So x squared minus 3x can be rewritten this way. This is useful for trying to put an equation y equals f of x of a quadratic into standard form. In the next presentation, we'll apply the concept of completing the square to put a quadratic into standard form, and then we will use that form to develop the quadratic formula. We'll also briefly look at equations of circles.